All right, welcome to video 7. Video 7 is focusing on the derivatives for logarithmic functions. Just like for derivatives of exponentials, we're going to focus on the natural number, e, and the natural logarithm, ln of x. All right, and so the derivative, we're just going to start with the rule. The rule is actually pretty clean, just like it is for exponentials. It says this, that if you want to derive ln absolute value of x, this derivative is equal to 1 over x, and this is true when x can't be equal to 0. All right, now when you look at this rule is a straight up definition. And again, it says if you have ln of x, then its setup is literally just 1 over x. Whatever that is, just 1 over x, done. That's its derivative. Now, the reason why we have the absolute values is that notice in its derivative, when I say 1 over x, for an ln, I can only take the ln of values from 0 to infinity. But when I look at 1 over x, this is everything but x equal to 0, meaning that 1 over x allows my x's to be negative as well. So to ensure that I'm using 1 over x completely, what the definition will do is list ln with the absolute values. So that way, if x is negative, it doesn't matter because the absolute value will make it positive, meaning that we can actually take the logarithm of it. Then it means that its derivative would be 1 over x. And so that's why, like, in the initial definition, what you'll always kind of see again is the absolute value listed. And then its derivative again is 1 over x for x not equal to 0. All right, just to kind of prove why this derivative comes out to be this way, what we're going to do is we're going to first let x be positive. So this means we can let f of x be equal to just ln of x, just the basic logarithm, like we did in the previous video. And what I'm going to do is I'm going to rewrite it as an exponential, or put it into its exponential form. All right, so remember that ln is log base e. So this would be x is equal to e to the f of x. And now I'm going to derive both sides. Oops, sorry, I was looking at the previous line. The derivative of x is just 1. And when I take the derivative of e to the f of x, remember that e to the f of x, its derivative is e to the f of x times the derivative of that power. So then this would be 1 e to the f of x times the derivative of f, which is just f prime. And this is where the trick comes in, and it really comes from our definition here, that e to the f of x is equal to x. So this means that I can replace e to the f of x with just a single x. And then by dividing that x over, we have that f prime, the derivative of the original function, is equal to 1 over x. And therefore we have a pretty straightforward proof. Now this proof, though, if you remember, is focusing, though, just for values x is greater than 0. The definition says that we're also letting x be negative. So if I needed to prove this another way, or letting x be less than 0, we need a way to go through and do that. And so I'm going to leave that up. It's a problem in the textbook. If you want to take a look at that further proof, go for it. It's optional. It's not really relevant to the calculus that we're going through and doing. If you were to take a regular Cal 1 next year in college, the professor would dive into the proof a little bit more. Because in Business Cal, we are worried about more applications and kind of dealing with the math. We don't go entirely into the theory for the derivatives in particular, especially with ln. So I'm going to pause in terms of the proof with that. Now, before we continue, what we're going to do is we're going to make one big assumption, and that's when we go through and we derive with an ln, I'm not going to continue writing the absolute value. We're going to go ahead and assume that x is greater than 0. and that means its derivative will be 1 over x. I won't have to do anything else with that, nor worry about the absolute values from this point on. All right, so we're just going to dive straight into some examples, essentially part A and part B. So find the derivative of each function. F of x is equal to x ln of x is for A. So I'm just going to copy that problem down. Now I want to find the derivative, so I'm going to derive both sides. So f prime is equal to the derivative of x ln of x. And when I want to derive something like x ln of x, I need to remember that this is essentially a product rule because I have one piece times another function. And so I need to go through and apply the product rule to this. So the product rule says derive the first function, which is x, times the second function, plus the derivative of the second times the first. So here's the product rule listed out. Then the derivative of x is just 1 times ln of x, plus the derivative of ln of x is 1 over x times x. And then now I'm just going to simplify. 1 times ln of x is just ln of x, plus 1 over x times x. These x's will cancel with one another, leaving me with just plus 1. This is the derivative f prime of the original function f of x. All right, so B. All right, this time I'm taking the derivative of g of x, which is equal to ln of x divided by x. Again, find g prime. I'm taking the derivative of this right-hand side. And this again is going to be a quotient rule. So I need to follow what the quotient rule says to do with this. So by definition, quotient rule says derive the top times the bottom minus derivative of the bottom times the top. And this is all divided by the bottom squared. So this is going to give me g prime. All right, so I'm just going to go through and simplify this and go through and do the derivatives. Derivative ln of x is 1 over x again times x minus derivative of x is 1 times ln of x. It's all over x squared. I'm just going to go through and simplify. 1 over x times x again. These x's are going to cancel. So in the numerator, I would get 1 minus 1 times ln of x, which is just ln of x, all divided by x squared. This is my solution. This is the equation for g prime in the first derivative. All right, and this is the first example. This is the first example, parts A and B. All right, so taking the derivative of ln is pretty straightforward. Again, the derivative of ln x is just 1 over x, and we'll just use the appropriate rules as we go. Now, just like with exponentials, what we found was that most of the time it's not just going to be ln of x, but it's going to be ln of f of x. So if I want to try and derive that, the rule that I have to employ here would be the chain rule. Now, the chain rule tells me to derive the outside, leave the inside alone, and then multiply by the derivative of the inside. So what that would look like then is if this is what I'm trying to derive, f represents the inside, and ln represents the outside. So when I take this derivative, the derivative of ln would tell me to do 1 over x. Well, that x again represents whatever's on the inside, in this case f of x. And then I would multiply, according to the chain rule, by the derivative of that inside piece. So in short, when you're deriving an ln that has a function on the inside, something more than just an x, it turns out that its derivative is the derivative of the inside over the original inside piece. And this is true no matter which ln, which logarithm that you're essentially deriving. Again, in particular, ln. When we derive this again, you're going to do 1 divided by the inside times its derivative, or because it's 1 times this we can just say the derivative of the inside over the inside. Now, of course, what we're assuming here, because it's ln of f of x has to strictly be positive. This is what you saw in the parentheses that I had to erase just to make some room for our rule and for our definition. All right, so you'll see an example here that I'm going to use. Find the derivative of the function f of x is equal to ln of x squared. So in this problem, this is my little f of x from the rule. And so I'm just going to flat out use the rule. All right, when I want to find the derivative, so I'm looking for f prime here. The derivative is the derivative of x squared plus 1. So I'll write that d over dx of x squared plus 1 divided by x squared plus 1, the original inside piece. So now I just need to go through and derive x squared plus 1. Well, that would be 2x according to the power rule, all over x squared plus 1. And that's it. This is the derivative of ln x squared plus 1. So again, it's the derivative of the inside divided by the inside. We take the derivative of that, and we're done. So take a look at example 3. Now, example 3 is a little bit more sophisticated. In that, it's not just ln of a single piece, but we actually have a multitude of pieces. Specifically, x squared plus 1 times x to the third plus 2 to the sixth power. So if we were to continue to work this problem like we've done in the previous one, the pattern would tell me that if I want to find y prime, I need to take the derivative of the inside, which is all of this stuff, x squared plus 1 times x to the third plus 2 to the sixth power, and then divide this by that what's on the inside, x squared plus 1, x to the third plus 2 to the sixth power. Now, don't try to simplify this, right? Remember, this top part I would need to derive before anything else happens. Notice that if I wanted to derive this, this would be a product rule with a quotient rule inside of it. So when it came time to derive this, I would have to then use, not quotient rule, sorry. I would have to use the chain rule for this part. And that just sounds disgusting because I would have to use product rule and chain rule. It'd be this long string of stuff. And so it doesn't sound very efficient in terms of using those rules. So what I want to do is go through and try to rewrite this into a better form and then use that form to take its derivative. Because again, the pattern for doing these types of LNs is so straightforward, is there a way to expand or rewrite the original function into a way that's just ln of a single parentheses, ln of a single little function piece? And the answer to that is yes. So if you remember from video 6, which was just logarithms and talking about those rules, this is why I took the time to cover logarithms again and kind of review those laws and look at them. All right, now I'm going to go back to the original function here, which is just y is equal to ln of x squared plus 1, x to the third plus 2 to the sixth power. And before I want to start looking at the derivatives, what I'm going to use is the laws of logarithms to expand this. So again, law 1 tells me that if I am multiplying on the inside of a logarithm like this, so remember that product rule that we saw when we came time to derive that, when I'm multiplying pieces on the inside, I am allowed to expand this into two separate logarithms where I add in between. Law 3 tells me that if I have a power on something that I'm taking the log of, I'm allowed to bring that power to the front. Notice that this logarithm just drops down because there's nothing else we can do with it. And so this is fully expanded. And so what I want to do at this stage is I want to go through now and derive this form, because it's taken away now the product and the chain rule that we had to worry about earlier. The derivative of the left-hand side is just going to be y prime. The derivative of ln of x squared plus 1 tells me to do the derivative of the inside divided by what was on the inside, plus 6 times the derivative of the inside divided by what was on the inside. The 6, remember, just stays out in front, and I take the derivative of this like normal, which is why I'm just going to leave 6 up top. And so now I just need to go through and derive these pieces. Y prime is equal to the derivative of x squared plus 1. Power rule tells me it's 2x. Plus the derivative of x to the third plus 2 is just 3x squared. And then I finish this problem by simplifying the 6 times 3x squared. And this is my derivative. We leave this, there's no need to make it into one big fraction. So using logarithms like this allows me, and using the laws, allows me to avoid having to use product and chain by applying this ln and extending it into a simpler form. Because again, the derivatives of ln's are pretty straightforward if it's just the derivative of the inside over the inside. Most of the time the inside pieces are just polynomials, meaning that we can go through now and just use power rule, which is very, very quick to use and very, very simple to use. All right, now let's take a look at example 4 and practice using this technique again. All right, so find the derivative of g of t is equal to ln of t squared e to the negative t squared. All right, so now this function, I'm just going to rewrite it. Notice again that I've got a product. I've essentially got m times n. So I'm going to expand this into ln of t squared plus ln of e to the negative t squared. I'm going to bring this 2 to the front. So I have 2 times ln of t plus, now here, this uses one of the properties with ln's and e's. The fact that ln and e are inverses means that these are going to cancel. What I'm left with is just this negative t squared. Everything's been fully expanded. We can now go through and derive. This would be 2 times the derivative of ln of t, which is 1 over t, minus 2t. So essentially, this becomes 2 over t minus 2t. Here, you'll see on my lesson plan that I went ahead and kind of brought this and made it into one fraction. So to walk you through that, I would need a common denominator, so multiplying top and bottom by t. I would get 2 over t minus 2t squared over t, which is 2 minus 2t squared all over that common denominator, t. And then the final step would be to bring out the 2. And this is the final answer. This final form here is just easier if I was to go through and find the next derivative. And actually, I don't even fully believe that. Really just kind of following what the book was doing. I would argue that this form is actually easier to find the second derivative if we needed to. And then going and continuing through the problem. Both of these answers are correct because they're both the same thing. But just to show you how you could simplify this down to one fraction, this is one way that you could do it. All right. So these previous two examples have really hopefully shown how useful these ln's and using the laws for ln's are. And so the question then kind of comes up of, all right, well, not every problem has an ln in it, but what if we could bring an ln into the problem, and then I can incorporate these rules and hopefully make the derivative a little bit easier to work with. All right, and so what that process is called logarithmic differentiation. So what it deals with, and you can see this in example 5, we're going to take a function that does not have an ln, where the derivative would be fairly complex, and by taking the natural logarithm of both sides, by inputting an ln into the problem, we can then help use my laws to make the derivative a little bit easier to work with. All right, and so here's kind of the steps or the process for logarithmic differentiation. The first step is to take the ln of both sides, and then expand using the laws. The second step is to derive, and then the third step is to solve for y prime, which is f prime of x. All right, and so let's look at example 5 so I can kind of illustrate what these steps are. So differentiate y is equal to x times x plus 1 times x squared plus 1. Now, if I was to derive this as is, notice that this would be a product and then another product. So I would have to use the product rule twice, which just does not sound appealing. So instead, what we're going to do is use this technique called logarithmic differentiation. Now, to get me started, I'm going to set y equal to f of x and use this notation for now. Now, the reason why I'm going to use this notation is for the next video, which you'll see on, I think, Friday, which deals with what's called implicit differentiation. All right, so this will hopefully make that bridge into that a little bit smoother by working this type of problem. All right, so I'm going to rewrite it as y is equal to f of x, so I'm changing that y. And then what I'm going to do is I'm going to take the natural log of both sides. So I have the natural log of f of x is equal to the natural log of x times x plus 1 times x squared plus 1. Now, by taking the ln of both sides, I can then use my laws of logarithms to expand this expression, essentially making it ln of x plus ln of x plus 1 plus ln of x squared plus 1, because they were all being multiplied together. On the left-hand side, I still have ln of f of x. At this point, now that everything's been expanded, all the laws have been used, I'm going to go through and take the derivative of both sides. Now, if you notice, and this is why I kind of wrote it with f of x, when I derive this left-hand side, this is using the chain rule definition that we had before. Right? I'm going through and I'm saying, what is the derivative of ln of f of x? Well, this derivative is f prime divided by f of x. Again, this is given by the rule above. I would encourage you to look back in the video if you want to see that definition again, but we had just gone through and used that. Now this is going to be equal to the derivative of ln of x, which is 1 over x, plus, now here I'd have to incorporate the chain rule, which tells me to do the derivative of the inside divided by the inside, since we're deriving ln, plus, and then the same thing, derivative of x squared plus 1 divided by x squared plus 1. All right, so I'm going to go through and take those derivatives. So I have f prime of x over f of x is equal to 1 over x plus the derivative of x plus 1 is just 1 over x plus 1 plus derivative of x squared plus 1 is 2x over x squared plus 1. And now this is where the third step essentially comes in. We've now derived, we have simplified as much as possible. Now I need to solve for y prime or solve for f prime. If you notice, I have f prime divided by f of x. So the next step is to multiply both sides by this f of x. So I'm bringing it over. So I have f of x times 1 over x plus 1 over x plus 1 plus 2x over x squared plus 1. Well, what is f of x? Well, f of x is the original problem. So I'm going to replace that f of x there with the original function. And I get that the derivative is equal to x times x plus 1 times x squared plus 1 times 1 over x plus 1 over x plus 1 plus 2x over x squared plus 1. And I'm done, because f prime is the derivative. It's y prime, which is what I was tasked with finding. We have now found it. This is logarithmic differentiation. So again, just to kind of run through the steps, I start by rewriting it in terms of f of x. We take the ln of both sides and then expand according to the laws of logarithms. Once I get everything expanded, I can then use the chain rule for ln's to go through and derive, giving me an f prime over f of x always, and then taking the appropriate derivatives and following the appropriate rules. Once I derive and simplify what I need to, then we multiply f of x to the other side, which we will always have to do, and f of x is always the original function. So I can substitute that back in, and I'm done. There's no need to multiply anything out. We are finished. All right, so in the final example here, I'll just kind of show you one more problem so you can see how it's done. And if you have any questions on this stuff, let me know. This is a fairly advanced technique, but this idea of taking the derivative of f of x, which is y, is going to come in handy a little bit later. So example 6 says to differentiate, so find the derivative of y is equal to x squared times x minus 1 times x squared plus 4 to the third. So again, I'm going to rewrite this as y is equal to f of x, which is x squared times x minus 1 times x squared plus 4 to the third. I'm going to introduce the ln to the problem by taking the ln of both sides. X squared plus 4 to the third. And now I'm going to use my laws of logarithms to expand this out. The left-hand side stays the same, but on the right-hand side, I would have ln of x squared plus ln of x minus 1 plus ln of x squared plus 4 to the third. Now, unlike last time, I actually have items raised to a power, so I need to bring the power to the front before I go through and derive everything. So this would be 2 ln of x. The middle term just drops down. There's nothing else to do with it. But the last term, I can bring a 3 to the front. Now I'm ready to go through and derive. So the derivative of ln of f of x, by definition, is f prime divided by f of x. This is equal to 2 times the derivative of ln x, which is 1 over x, plus the derivative of the inside, which is x minus 1, all over x minus 1, plus 3 times the derivative of x squared plus 4, all over x squared plus 4. And then now I'm going to go through and simplify, derive and simplify the tops. So I have on the left, just drops down. 2 times 1 over x is just 2 over x. The derivative of x minus 1 is just 1. 3 times the derivative of x squared plus 4. That derivative is just 2x. And then now I'm going to go through and solve for f prime by multiplying f of x over. Bring down all of this junk, where 3 times 2x is 6x. And I need to re-plug in for the original function. So I get f prime only in terms of x, which in this case, just having to look back, f of x is x squared times x minus 1 times x squared plus 4 to the third times all this junk in parentheses. But what all this equals is the derivative of the original function. It represents its rate of change. And one thing just to kind of highlight here is you may look at this and say, this was gross. Like, why not skip over logarithmic differentiation and just derive what the original function was? Well, if this is what the logarithmic looks like, and I'm telling you this is one of the most efficient ways to do it, if you were just to derive this as is, it's going to look way grosser than this one ever would. As an exercise, if you want to try it, I would encourage you to go through and try to find this derivative using the product rule, chain rule, or quotient rule if necessary, and then to look at our work. For doing the logarithmic, we were able to do it in a couple lines. I guarantee you the product and chain rule would take you more so, depending on the level of comfort you have with it. So logarithmic differentiation is a really clever technique. It's a really useful technique. and it's one that I would encourage you to go through and do. But again, at this stage, we are done with this. So if you have any questions over derivatives of logarithms, specifically ln, that's all that's all our focus will be on. And then with logarithmic differentiation, let me know. We'll have a virtual class available in between videos, and then we'll have one more video for Friday. All right, so thank y'all, and let me know if you have any questions.